Okay, so we will be recording this portion of the session. If anybody has any objections with recording, please say so now. Okay, if not, then we will continue. Okay, so we are going to be using Simulink to represent the antenna azimuth system, which is this one that we're looking at here with configuration 1. We're going to be representing this using Simulink. Now, what is the difference between Simulink and Matlab? Simulink is a part of Matlab. It's one of the various tools that we have in Matlab. And basically with Simulink, we can represent models, and it's a graphical representation of models. If you guys have used LabVIEW, or if you've used Multisim, you're going to notice some similarities there. So I'm going to launch Simulink here. And once we launch Simulink, we've got the screen here where we've got the different options. Before I continue, I am also going to launch the file azimuth params config1. Remember that these files, you may find them in Blackboard. And so what we're going to do here with this file is that I'm going to close Simulink here first. We're going to run this file just so we have the configurations, just so we have the configurations loaded of the parameters. So just so we have the parameters loaded, because we're going to be using those parameters in the model. And if we don't have them defined in the Matlab environment, then there's going to be we're going to get some error messages there. Okay, and so I've run this, and now I am going to open Simulink. And opening Simulink here, I'm going to be opening a blank model. And when I open the blank model, I get this canvas here. And basically what we're going to be doing is that we're going to be building the azimuth antenna model, which is basically this one that we have here. We're going to be building it as a block diagram, and we're going to be able to represent it as a block diagram. And so the first thing that we have here in the block diagram is the pot. This block here that says potentiometer, K pot, which is the input pot. That's going to provide the angle that we want for the antenna. And so we're going to go over here to the library browser. And here in the library browser, we can see the different blocks that we're going to be able to use in Simulink. And so we're going to be using basically, I'd say 1, 2, 3, 4 major categories here: the commonly used blocks, the continuous, the sinks, and the sources. So here in continuous, we're going to have different blocks that are used for continuous system analysis. The one that we're going to be interested in here is this one that says transfer function. Basically, the transfer function block is going to be able to represent a transfer function, and it's going to be represented the same way we represent it in Matlab, which is basically, this is an extension of the TF function, where we represent the transfer function as a vector with the coefficients of the numerator and a vector with the coefficients of the denominator. Notice also that we have a block here with a PID controller. We're going to be using that further on. So I'm going to bring the block over here. I'm going to place it in the canvas and place it here. I'm going to double click, and the numerator coefficients in this case is going to be K pot. Since this is a constant, then the denominator coefficient is going to be a 1. And we click OK, and we get the transfer function for that. I can change the name. I'm going to call this input pot. And that's the way I've defined it. Now, if it's a constant, we're going to have the constant divided by 1, just because of the numerator denominator structure. Please, and if you have any questions, please raise your hands and we'll stop. The next thing that we have here in the diagram is a summing point with a plus and a negative that's going to represent the feedback. So we're going to go over here and we're going to go over here to commonly used blocks. And there's an option here, a block that says sum, which is a summing point. We're going to bring that over here, place it in the diagram, do a connection here. And notice that by default, the summing point is basically a block that's used to add two signals. But since this is a negative feedback, remembering that the negative feedback, we have a negative value. So we're going to double click here. And instead of the list of signs being plus plus, it's going to be plus minus. And that way the summing point is a point that does a difference. The next block that we have here is the preamplifier, which is a constant K, the constant K that we had defined previously. So again, we're going to go back here to continuous. We're going to grab a transfer function, bring it over here, place it here in the diagram, do a connection. And this transfer function is going to be the preamplifier, which is going to be K. And the denominator is going to be a 1. Now we're going to call this preamplifier. Next up in the diagram, we have the power amplifier, which is K1 divided by S plus A. So we grab a transfer function block, we bring it over here. We connect this, and we're going to have yes, go ahead, Daniel.
There's a quick shortcut for what you're doing right now, just for the arrows. When you place a new block, you see there's like a blue, arrow that creates. You just have to click it once. It's gonna create the arrow, the connection, or like you won't have to manually draw the arrow all the way.
Yeah, no, thank you, Daniel. I actually know that, but I'm trying to be as descriptive as possible because of the recording. I'm just trying to do the kind of like a Lego thing. But yeah, thank you, Daniel. So basically, it's very similar if you've used Multisim and other softwares where you've got blocks and do connections. If you place it close to the block, it's gonna sort of like a phantom connection is gonna appear, and you can just click it and it's gonna connect. So that's correct. Thank you, Daniel. And so for the power amplifier, it's going to be K1 divided by S plus A. So we're going to have a K1 divided by S plus A. And remember that we're using the coefficients. So the coefficient of S is 1. The coefficient of A is A. So it's going to be S plus A. And we're going to have it like that. Okay. Next up, we're going to bring another transfer function here. And this is what Daniel is saying. We just double click there and it connects. Oh, I didn't name this one. This is going to be the, what is it? Power amplifier. Power amplifier. Next up is going to be the motor and load. I'm going to put the name down there. The motor and load. And here for this one, notice that we have S multiplied by SAM. This is the same as having, we need a polynomial. We need a complete polynomial, not polynomials that are multiplying, at least not for Simulink. So this is equivalent to having S squared plus AM multiplied by S. And actually we have plus 0. And so the coefficients are going to be 1, AM, and 0. And if we go back over here to Simulink, we're going to click, the numerator is 1, the denominator is going to be 1, AM, and 0. And remember that these parameters, the K pot, the K1, I've already defined them in the configuration parameters file. So it's important to have them defined in the workspace. If not, then these blocks would appear with an error, okay? Notice that it says num den. Generic, that's just because the box is too small to show what I wanted to show. So I just make it a bit larger here. It's a bit too large. There we go. Oh, and it's KM on the numerator. We have to have a KM here. So I'm going to make a mistake here. I'm going to say K. So if I do that, notice what happens. The block turns red, and there's a mistake here that it doesn't recognize the parameter I put there. That's because it's not defined in the workspace. It's important to have them be defined in the workspace or define them at some point. So I put KM, and now it turns blue again. Remember, if anybody has any questions, please let me know. The next block here is the gears. So we're going to come over here and we're going to do another transfer function, and we're going to say the gears are KG, and the denominator is going to be a 1. We'll do a connection here. Okay. Next up is the output, and then we've got the feedback over here to a pot, to a pot, which is actually this same one that we have here. So we can just actually copy paste it. I just did a literal Control-C, Control-V copy paste. But notice that, and I'm going to name this differently. I'm going to call this measurement potentiometer, because this is the one that's going to be doing the measurement. However, I need it to be facing the other way, because now the block is going from, it's not going from left to right, it's going from right to left. So there's an option here. If we do a right click, there is an option here that says rotate and flip. So I'm going to do a flip block, and basically the block gets flipped. So the input now is on the right, the output is on the left. And so what we do here is that we're going to do a connection. Do a connection over here, and then this connection comes over here. Okay. And basically we've just represented the block diagram. What's missing? The input and the output. Now for the input, what we're going to do, there's various types of inputs. Inputs are going to be the sources, I'm sorry. Inputs are going to be the sources. And so there's a great variety of sources that we can use. And so there's many types of inputs or stimuli that we can give the system. Noise, constants, chirp signals, clocks, pulses, repeating sequences, random numbers, a ramp, sine wave, step. We can actually build a signal that has different sections to do different types of simulations, a waveform generator. The one we're going to be using is the step function. I'm going to bring that over here, and I'm going to bring that over here. And the step is going to be connected here. Now, the step function is basically going to be defining a step or a constant that we're going to be giving, just for the purpose of the example. I'm sorry. If we double click this, there's some default values. So the initial value is 0, the final value is 1, and the sample, there's a step time here that for Simulink, the step time is going to be the initial time that's given. So if we simulate this with a step time of 1, actually the step is going to begin at 1. So the step time is the time where the step is going to begin. So we actually want to simulate this starting as close to 0 as possible, but we can't give it a 0 because it doesn't accept it. So we just give it a very small value. You can give it as much zeros as you want. You can exaggerate that if you want, if not. And lastly, for the output, we want to be able to plot somehow or visualize the output. And so what we're going to do there is that we're going to grab a sink. The sinks are going to be these outputs where we're going to be sending the signal. So there's many sinks that we can use. I'm going to use a simple scope that I'm going to place here. And the scope can have many inputs, by the way. And we're just going to do a connection there. The scope here has properties that we can modify if we want. Signals and ports. If we wanted, we could add another input. I'm going to do that. I'm going to add another input, by the way, and I'm going to do this. I'm going to bring this over here. I'm going to exaggerate this a bit. And I'm actually going to connect the, input also, so we can see both of them in the same scope. Once we have this, questions with this before we move on. Was it relatively clear how we built the block diagram? And so next up, we can do a simulation. Now here we have the simulation time, okay? So right now it's set to 10. I think 10 is fine. That's the simulation time that we're gonna give it. And I'm gonna run the simulation. And it's going to run the simulation. If there were any errors or anything that would have appeared, or any of the blocks were red, it would mean that we couldn't run the simulation because there's some sort of error going on there. So after we run the simulation, I can double click the scope and we're going to see the simulation. The blue is the step input, and the yellow is the output of the system. And for a gain of 100, we had already seen this example previously. We see that there's an overshoot, and then there's a setting time over here. We can do many things here if we want to analyze this signal, and this would be the output. I'm going to jump over back here to Matlab, and I am going to run the original model that we had, and this one is the file that says Azimuth Matlab code. This is the original one that we had previously, so it runs the configuration first, then it's the definition of the different blocks, then it runs the simulation, and it runs the step. Okay, this, you can find this file also in Blackboard, and it's basically doing this, which is the definition of each of the blocks, and then running, doing the closed loop, and then running the simulation as a step. I'm gonna run this one. I'm gonna give it the same value of 100, and we get the transfer function, and we should get the graph here. And I'm gonna bring this over here. And I'm going to bring this over here. So what we have here on the left is the Simulink simulation. Okay. What we have on the right is the Matlab simulation. Notice that the graphs are the same. Over here on the Matlab one, we can identify certain values that are going to be important to us, like the peak response. We can also identify the setting time, which was going to also be of interest to us. We could identify the rise time, which would also be of interest, and also actually the steady state value. Over here, we can also identify values in the graph, but the difference with the Simulink one is that we actually and literally have the block diagram as a model that we can use, and we can play around with it, giving it different signals and seeing how it reacts. And it's actually a more visual and graphic representation of the system. And so we're going to be using both of these for the next few exercises that we're going to be doing for system analysis and design. We're going to be using these. We're going to be using both of these tools, both MATLAB and Simulink. Some people are more familiar. I'm sorry, not familiar. Some of you are more or feel more at home using coding. So some people like to code. I prefer to code, frankly, but I'm not against doing the more of the graphic thing. Some of you might prefer, if you work with Multisim or LabVIEW, prefer more of the block diagrams things, be able to represent it that way. Either way, both in the end use MATLAB as the basis, and both are using MATLAB code in the end. Okay. Now, questions with this example. Remember that the previous example, the one we did, is in we also recorded that one, so you can review it. So questions with the Simulink version? Nope. Okay, all these
No.
files, the files that I used right now, all of the files are in Blackboard. You can download them from Blackboard and run them directly in Matlab. Okay.